All right, guys, let's start. Okay. So if you have any question, you can type in the chat window. Okay. A couple of things before the start of the lecture. Okay. So the first is the quiz. Okay. So I'm still the reviewing the quiz. Okay. So hopefully it can be done by tomorrow. Okay. I don't know. Okay. So because the quiz 3 has more former drawing questions and also the mechanism question. Okay. So that's take much longer time. Okay. And then the second thing is kind of the lab. Okay. So from your lab 4 this week. Okay. So you guys will be graded based on kind of your product yield and also the purity. Okay. So that's you need to be careful. Okay. So don't want kind of knock over your kind of wire. Okay. Or kind of the break your glassware. Okay. So, and then nothing. Okay. So if that happens, you can of lab 1 to 3, okay, that's fine, okay. But from lab 4, 4, 5, 6, okay. So just keep in mind, okay. So you will be graded based on kind of the yield and also purity. Purity pretty much kind of just based on any mark, okay. All right, okay. So let's the continue chapter 17, okay. So again, if you have any question, type in the chat window, okay. All right, so 17, last time we talked about kind of directing effect. Okay, so normally speaking kind of electron donating group. Okay, so also para directors. Okay, and hydrogen. Okay, although it's kind of electron withdrawing group. Okay, so also is kind of also para directors. Okay, and for all the other kind of electron withdrawing group. Okay, so it will be kind of meta director. Okay. And here I will use some kind of energy diagram kind of a little bit the top of this issue. Okay, so last time we try to use kind of the resonance structures. Okay, show more stable kind of the resonance structure. Okay, so think it here kind of energy diagram. Okay, and so this one actually already talked about. Okay, so for the RQ group. Okay, so RQ group itself, although won't donate electron into kind of ring. Okay, but once okay, so let's draw it. Okay. Some RQ group. Okay, but once you have some kind of positive charge, you have kind of also para directors. Okay, so if you have something group goes also para positions. Okay, so you can end in kind of something like this. Okay, so the positive charge on kind of carbon with the RQ group attached. Okay, and then you can so for example we go to kind of also positions. Okay, so right, and then the RQ group. Okay, can donate somehow kind of electron into the ring. Okay, stabilize this the intermediate. Okay. So that's why RQ group is kind of also para directors. Okay, although it's cannot donate lone pair electrons. Okay, right. And but if it's if the kind of the meta substitute situation. Okay, so you bypass this kind of stable intermediate. Okay, and then you won't get kind of kind of the actual benefit from kind of the RQ group. Okay. Right, and then that's a similar thing for all other kind of electron donating group. Okay, so pretty much all the electron donating group. Okay, so stabilize the intermediate. Okay, and then lower the energy. Okay, and then no matter it's kind of also para or kind of meta directors. Okay, but the compare these two situations. Okay, so also para can stabilize more. Okay, so let's show the energy diagram here. Okay. We can see kind of also para kind of the intermediate kind of the much lower energy. Okay, so should code kind of the intermediate here. Okay, and then make the energy barrier also lower. Okay, compare with meta. Okay, so that's the reaction goes kind of lower energy pathway. Okay, that's okay kind of also para directors. Okay, right, here's kind of little bit I put all the three situations together. Okay. Right. So that's the delta G, free energy change. Okay. And then assuming kind of we all compare it with kind of the bending. Okay. Right. So that bending can actually set up kind of the standard. Okay. So we can treat that kind of zero energy one. Okay. All right. So if it's kind of electron donating group. Okay. So it's will lower kind of the kind of the energy barrier, okay, and then make it reaction faster, okay. So in this case, doesn't matter the also para or kind of matter, okay, both going lower, okay. But here also para kind of the lower than matter, okay. So that's why reaction goes here, okay. So that's here for the electron donating group, okay. Yeah, leave some space, okay. So we put more here, okay, here. Okay. Okay, and then we come kind of the deacting group, okay. So yeah, like nitrile, okay. So nitrile, okay. So we are the first kind of make a reaction much slower, okay. So that's shown here, okay. So we are 10 to 7 times kind of slower than benzene, okay. And the second kind of it's kind of the meta director, okay. Reason for that kind of although doesn't matter kind of also para or kind of meta, okay. So all the situation kind of raises the energy and makes the reaction slower, okay. But because the also para gets kind of one extremely unstable intermediate, okay, and then eventually kind of rise energy more than kind of meta kind of directing, okay. So because you can see kind of Mata has kind of a bypass here, extremely unstable kind of intermediate. So this positive charge kind of the bypass here. Okay, so that's here the relative comparison kind of the lower energy comparison the also para. Okay, so now we go here. Okay, so still two situation. Okay, and then one also para and one kind of mata. Mata kind of the relative kind of the lower energy. Okay, although both have higher energy than benzene. Okay. So that's the typical kind of electron weight joint group. So that's also showed here, okay. Yeah, the energy with all comparative is kind of bending, substitution situation, okay. All right, and then last one kind of very tricky thing kind of halogen, okay. So for halogen, normally speaking, kind of there are two effects, okay. So for the reaction rate and also the residual chemistry, okay. So one called kind of inductive effect, okay. Another called kind of resistance effect, okay. So normally speaking, kind of the full reaction rate, okay, determined by kind of inductive effect, okay. And so inductive effect of the electron donating or kind of accepting, okay. So in this case, if we have kind of a halogen, okay, in the benzene ring, okay, hydrogen has higher electron negativities, okay. So in this case, pretty much a poor electron wave from benzene, okay. So that's why the halogens kind of the electron withdrawing group, okay, and also the active group, okay. And so that's the halogen, okay, because the inductive effect, okay. So that should be kind of the active group, okay. But here another tricky thing about kind of halogens, kind of halogen itself has kind of lone pair electrons, okay. All right, so for example, we have positive charge here, okay. That's a positive charge, okay. And then, so once you do some kind of the ES reaction, generate kind of carbon cation, once the positive charge, shape to kind of carbon with hydrogen attached, okay, and then you can do the resistance, okay. And then more resistant and more stable, okay. So in this case, when we come kind of residual chemistry, okay. So actually kind of the resonance effect outweigh kind of inductive effect, okay. And then only also para can have this kind of intermediate, okay. So that's why kind of the halogens can also para directors, okay. So that's the very kind of the tricky thing, okay. So in another way, okay, we see the kind of for the halogen, okay. So reaction kind of much slower, okay, and then it should be kind of the inductive effect kind of outweigh kind of resistance effect, okay. So determine reaction rate, okay. But when it comes kind of residual chemistry, okay, so the resistance effect outweighs kind of inductive effect, okay, and determine kind of the location of the second subgroup positions, okay. And if you try to explain it kind of from energy diagram, okay, so pretty much like this, okay. Still two situations, okay. So for the halogen case, so both the meta and also para kind of the higher energy than kind of the benzene, okay. But the meta has higher energy than can also para, okay. Right. So that's the halogen, okay. So in this case, if you do ES reaction always go to kind of lower energy, kind of the state, okay, here, here, here. Okay, so that's why kind of the very special kind of the directing effect. Okay. All right. And so here's kind of the little bit of summary of we talk about on the directing effect. Okay, so just not only you have to remember all these guys kind of it's auto para director or kind of activating, deactivating. Okay, so we have to remember that kind of ranking. Okay, so because later we have kind of multiple substitution situations. Okay, so the higher on this table kind of the stronger activating group. Okay, so for example the OH or kind of the amine. Okay. And then following my kind of amide or kind of ester or kind of other kind of situation, okay, and then followed by kind of RQ and also benzene, okay, and then followed by hydrogen, and then followed by kind of carbonyl compound. Eventually, some kind of strongly kind of directing group, okay, so nitro, sulfuric acid, kind of some kind of positive charge species, okay. So that's I'm sorry, you have to kind of try to memorize all this, okay. RQ just can keep in mind a little bit of special situations, okay. And because of this kind of directing effect, okay, so when we kind of see certain compound, okay, so you want to put two substance group on kind of the benzene ring, okay, through kind of ES reaction, you have to consider that kind of regiochemistry and those are kind of the directing effect, okay. For example, okay, so we try to put kind of chlorine and also a nitro group, okay, onto benzene, okay. So if we do the nitration first, okay, and because the nitro groups kind of meta directors, okay, so if you do kind of the chlorination, okay, so that's you put kind of the chlorine on kind of its meta position, you get kind of I'm chloronitrobenzene, okay. All right, but if you do the reverse order, okay, so you do the chlorination first, okay, so and then because the chlorine is kind of also para directors, okay, so you get kind of p-chloro kind of the nitrobenzene. Actually, there's another compound that should be kind of O-chloro-nitrobenzene. Okay, so because the chlorine kind of also para directors. Okay, so that's you have to think about it. Okay, so and later this chapter, okay, and I will summarize kind of thesis kind of the design kind of the strategy. Okay, so we use a lot of this kind of directing effect. Okay, all right, and now we take a little bit of practice, okay? So all right, so try to finish this reaction and also this reaction, okay? Draw the product for both reaction, okay? Here's the oxygen, okay? Give you guys 1 minute. Right, so here are these two questions, okay, two reactions. Use the knowledge we learned about kind of also para and also meta director kind of the directing effect, okay. For these types of question, okay, so the most important thing kind of don't do like kind of reaction condition. That's just kind of put something onto benzene to put something. Okay, so the most important of what's already on the benzene, okay. So that's determine kind of your position for the second kind of ES reaction kind of second group, okay. All right, okay, let me go through kind of one by one, okay. All right, so first, okay, so you see kind of this is kind of ketone, okay. Ketone you look at here, okay, so ketone is kind of moderate kind of deacting group, okay. So this kind of meta directors, okay. So that's in kind of when you do the chlorination, okay, so the chlorine should go is kind of meta positions, okay. Yeah, like this, okay. So certainly you can draw also on here, okay. So that's also meta position for the this ketone, okay, but it's kind of pretty symmetry, okay. So that's the same thing, okay. Right, and then next to come kind of the ethyl benzene, okay. So this ethyl group, okay. So that's the also para directors, okay. Also para directly, and then we do FC kind of acylation reactions, okay. So we put the acyl group on the benzene, okay. So para directors, also para directors, okay, because they're the acyl group, okay, so normally quite bulky, okay. So major product, okay, show like this, okay. And this is okay, if you want to write down, okay. And so that's a little bit a unique thing for the acyl, the group, okay. Friedel-Crafts acylation reactions, okay. Friedel-Crafts acylation, normally speaking, kind of you have very bulky kind of the acyl group, and then major product should be kind of the para, okay. Major should be para, okay. But in exam the quiz, okay. So if you draw kind of product at also position, okay, probably I still give you some kind of points, okay. So but major keep in mind, okay. So that's the goes kind of the para position, okay. So that's only true for the kind of the Friedel-Crafts acylation reactions, okay. So because the acyl group kind of too bulky, okay. So for all other kind of free kind of the ES reaction, okay. So can go both also and para, okay. Right, and then for the also para directors, okay. So we can have two compounds, okay, two products, okay. So theoretically speaking, okay. So because each the benzene has kind of the two also and then one para, okay. So theoretically speaking, kind of also the substitute product should be kind of two times kind of the para substitute product, okay. But the reality is kind of if we have kind of very bulky group, okay. So normally speaking, kind of also should be kind of a little bit disfavored by the steric hindrance, okay. And then the ratio of also to para kind of less than 2 to 1, okay. So here's kind of we have the tolling methyl group down here, okay, and then also it's kind of 60% and then 37% kind of para, okay. So not exactly 2 to 1, okay. So if we further increase kind of the first second group on the benzene kind of increase its size, okay, for them kind of this T group, okay, and then further decrease kind of this ratio, okay, also to para, okay. So for example here, okay, so we do kind of the nitration for this T-butyl benzene, okay, and then the also only 18%, okay, and then para become kind of the 28%, okay, 82%, okay. So that's the something you just keep in mind, okay. All right, okay. So now we come to kind of the most difficult part for the today's lecture, okay. So multiple kind of the substitution, okay. So what's that mean, okay? So if there are kind of two or more kind of substitution group already on the benzene, okay, and then if you want to do the third or fourth EAS reaction, okay, where's kind of third or fourth kind of substitution group goes, okay. So you have substitute group 1 and substitute group 2, okay. So you already have 2, okay. And then you want to do the kind of another EAS reactions, okay. So now where this one goes, okay. So we have full position open, okay. Where it goes, okay. So that's the tricky thing, okay. Right. So if the two group have the same kind of direct effect, okay. So the result will be additive, okay. So what's that mean, okay? So those show here, okay. Yeah. Okay, so this is kind of the two nitro toluene, okay, already has the two subgroup on the benzene, okay, methyl and also a nitro group, okay. So at the 1-2 positions, okay. So we try to do nitration for this compound, introduce the second nitro group onto this benzene ring, okay. And so now we have to look at kind of these two subgroup direct effect, okay. So for the methyl, okay, so that's here the also para director, alkyl group, okay. So it's one here the alkyl group, the second nitro group goes kind of it's also para directors, also para positions, okay. Should be kind of 4 and 6, okay. And the nitro group is the meta directors, okay. So in this case, yeah, it's one kind of the second nitro group goes kind of also 4 and 6, okay, because that's kind of meta position for this here the nitro, okay. So that's pretty much means kind of these two cycle group have same kind of direct effect, okay. So that's reinforced, okay. So yeah, in this case pretty much the dominant species kind of at 6 and also the 4, okay. So only 1% kind of goes kind of 5, okay. So that's the same kind of direct effect, okay. But quite often happen kind of two subgroups have opposite kind of directing positions, okay. And so for example here, okay. So we have kind of methyl and also nitro group kind of 1,3 disubstitute, okay. So yeah, and so want to do kind of second kind of nitration reactions, okay, and then put the second nitro group on bending, okay. And the methyl group, okay, so yeah, it's also para directors. One here the nitro group goes kind of 2, 6, 4, okay. So that's kind of also and para positions, okay. But for the nitro group, okay, nitro groups kind of the meta directors, okay. It's want to go to kind of the 105, 5, 1 is already taken by methyl, okay. So that's been kind of should go 5, okay. So the all these two groups have the different kind of directing kind of the positions, okay. So that's the just remember, okay, the stronger activator control, okay. So that's somehow kind of important, okay. So write it down, okay. Stronger activating group, okay, controls the radiochemistry, okay. All right, so what's that's why I ask you guys kind of have to memorize the ranking, okay. So the ranking go this direction, okay. Yeah, that's right, okay. Yeah, the methyl group will control, okay. So you can say kind of methyl belongs kind of alkyl group, okay, and then nitro goes here, okay. So that's methyl is kind of the boss, okay. Methyl tell kind of where's second again nitro group goes, okay. All right, so that's the show you here, okay. So the nitro groups goes kind of also para position of the methyl, okay. So so this is the boss, okay. This is the boss, okay. And one goes kind of the 2, okay. So this position, okay. So because the 2 positions kind of 2 bulky, although it's kind of also position to the methyl, okay. So but the kind of 2 group surrounded, okay. So that's why kind of no 2 substitute, okay. So right. So normally speaking, kind of if you have 1 electron donating group, 1 electron withdrawing group, okay, always kind of electron donation group, okay, control kind of the radiochemistry of the ES reactions, okay. But if you have 2 electron donating group, okay, then the stronger kind of electron donating group, okay, or kind of the highly kind of activated kind of group, okay, control the radiochemistry, okay. And give you guys 1 example, okay. All right. So for example, we have this here the p-bromo kind of phenol, okay. All right. So try to do the sulfonation. We try to put the sulfonate group onto benzene. All right. So that's here if you take a look, okay. So we have for the bromine belongs kind of the halogen, okay, and then OH the kind of the both kind of the also para directors, okay, and then for the bromine, okay, once the sulfonate group goes is kind of also positions, okay. So para is blocked, okay. One go here, okay. But for the OH, okay, so once the sulfonate group, okay, goes it's the also positions goes here, okay, here. All right. So now you have to remember which one's kind of both, which one has kind of a stronger activating group, okay. All right. So OH kind of strongly activating, okay, so that's here the much higher rank than kind of bromine, okay, so that's been kind of OH is the boss, okay, so that's determine kind of where the sulfonate group goes, okay. So the final product should be like this, okay. Right, sulfonate keep in mind SO3H, okay, so that's here the right kind of the substituent group, okay. Yeah. All right, okay, so so please remember this the chart, okay. So now you guys take try, okay. Try to work on these two questions, okay. All right. So this is the chlorine, and this one kind of methoxy group, okay. And then second one, okay. All right, so take practice. Yeah, work on these two reactions, okay. Yeah, so far you can try to look at this chart, okay. So determine which one's kind of the stronger activating group, okay, and which one's kind of boss, okay. But later in the exam the quiz, okay, future exam quiz, okay. So you have to use this kind of chart, kind of memorize this chart, okay. So use kind of quickly, okay. For the second question, okay, so the ask kind of nitration reactions, okay. So normally speaking, nitration reaction we put kind of the nitric acid and sulfuric acid, okay. But sometimes okay, so in the questions, okay, so the directly provide you kind of the electron file, okay. So that's nitronium, okay. So that's actually kind of make your life kind of easier, okay. Let's do this, okay. 1, 2, 3, 4. 1, 2. All right, okay. Yes, that's right. Okay, so if it's kind of also para, you need to draw balls, okay, especially kind of for the small subsystem group, okay. For the bigger one, Friedel-Crafts oscillation, okay, probably you draw the para should be fine. Okay. All right, so let's go through these two, okay. All right, so we try to do kind of bromination for this compound, okay. So type in your chart window, okay. So where's the bromine goes, okay. So go to 1, 2, or 3, or 4, okay. All right. And then second one also, the same thing, okay. So we try to do nitration, okay. So the where the nitro group goes, okay, 1 or 2, okay. So type in chart to window, okay. That's right, okay. 2 and 4 for the first one, okay. Yeah. So in this case, the methoxy group, okay. So that's the boss, okay. So it's kind of higher activity group, okay, than the chlorine, okay. So that's the determine kind of the where the bromine goes, okay. So because the methyl group kind of also para reactors, okay. So in this case, we can have kind of two compounds, okay. So one's gonna go to the two positions, okay, Br, okay, and another one goes kind of it's the also positions, okay. Yeah, goes to 4, okay. Right, so that's here. Right, and then for the last one, actually kind of easier, okay, because the CF3 kind of meta directors, they want to go kind of 2, okay, meta positions, okay. Methyl group, okay, also kind of the kind of also para directors, okay, but also want the stress group go to it's kind of also position, okay. So that's kind of these two have same kind of direct effect, okay. So eventually, okay, right compound should like this. Okay. So next kind of here we'll study some kind of here that we call the you guys got this or why does the science directly second problem? Okay. Yeah. So this is also para-directors, okay? So it will direct into kind of here and here and here, okay? And then for the CR3 meta-directors, okay, also want to go these two positions, okay? So this is the first situation, okay? So two groups kind of the reinforced, okay? But if these two have kind of the opposite kind of the direct effect, okay? So methyl group will control, okay? Yeah. All right. Okay, so now we move to kind of the ES reaction for the polycyclic and aromatic compound. Okay, so we only need one. Okay, so that's the for the we call the naphthalene. Okay. Right. So naphthalene has kind of the two benzene ring kind of fused together. Okay, and share kind of two carbons. Okay. And then if you want to do ES reactions, okay, so for the kind of bromination, okay, so actually you don't need to even add catalyst, okay, so for the benzene we have to add kind of the iron bromide, okay, but for the naphthalene, okay, you don't need to add iron bromide, okay, because this one kind of too electron rich, okay, so too easy for the reactions, okay. All right, so now come to questions, okay, where it goes, okay, so that's that got a little bit confusing, okay, so because there are kind of total 8 open positions, okay. So we do this 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. So the for the reality, okay, so the should go to kind of the 1, 4, 5, 8. Okay. So so 1, 4, 5, 8 kind of symmetrical to each other. Okay, doesn't matter where you want to put the bromine. Okay. And the narrow goes kind of 2, 3, 6, 7. Okay. So that's the thing you guys just keep in mind. Okay. A reason for that kind of not required, okay, but if you like, you can go home, kind of try to draw the resonance structures, okay, try the resonance structures, okay. So if the bromine goes kind of 1, 4, 5, 8, okay, so you can draw probably like 5 resonance structures, okay. But if it goes kind of 2, 3, 7, 6, okay, so that's only draw like maybe 3 resonance structure. So last the resonance structure compare with kind of the 1, 4, 5, 8, okay. So so for you guys, just remember, okay. So the naphthalene, okay, go to these positions, okay. Any of these carbon will be fine, okay. All right. Okay, and then now we talk about another interesting thing about kind of the aniline kind of ES reaction, okay. So aniline has the NH2, okay, on the benzene ring, okay. So NH2 kind of amine, okay. So amine theoretically speaking kind of the first number 1, okay. So that's the very strong kind of activity group, okay. So prefer ES reaction also para-directors, okay. But for the reality, okay, so now the 5 ES reaction work for kind of aniline, okay. So no matter bromination, sulfonation, kind of the FC acylation, FC acylation case, now the work, okay. So why is that case? So because the aniline is kind of the base, okay. Both the bronze is kind of base and also loose base, okay. Also very good nucleophile, okay. So in this case, if you want to do kind of the sulfonation or nitration reactions, okay. So you have to use acid, okay. So that matter kind of sulfonation or kind of the nitration, okay. So so this is the base, okay. So that's the acid, okay. So before the kind of FC, the acylation, acylation, the for the nitration kind of the sulfonation happen, okay. Acid-base reaction will happen first, okay. Yeah, you turn kind of some salt, okay, and then totally change the nitro group, okay, from most active one, okay. So you see kind of most active one to the most kind of deactivated one, okay, and also kind of the killed all the regions, okay. So that's why kind of cannot do sulfonation and also nitration reactions, okay. So why is cannot do kind of bromination, FC, acylation, FC, alkylation, okay? Because those reactions require use kind of Lewis the acid as kind of catalyst, okay? So but the nitro group, okay? So it's kind of the amine groups kind of very good kind of the loose base, okay? Loose acid, loose base, okay? So that's here we have it here like this. H2, okay, and then we're trying to kind of this kind of complex, okay, and eventually kill all the catalysts, okay. So that's also kind of work, okay. And also, okay, so because amine group kind of good nucleophile, okay, so can do kind of substitution reactions, okay. So in this case, if you react with kind of try to do kind of FC acylation reactions, okay. Somehow kind of substitution reaction happen, okay. So so for this reaction, actually kind of we'll learn later, okay. So and then convert it to kind of the amide, okay. So this reaction, you don't need to know it down, okay. Similar situation kind of if you want to do FC alkylation reactions, okay. So SN2 reaction will happen, okay. FC alkylation we use kind of the alkyl chloride, okay. So same thing, okay. So Keep group, okay. So that's we learned kind of in the previous chapter. We called kind of directly alkylation, okay. So in this case, none of the ES reaction work, okay. So although amine group kind of strong activity group, okay. All right. So so to do kind of so that's actually kind of we use kind of strategy called kind of the protecting group, okay. So protecting group kind of you have two functional group in one bonding, okay, in one kind of molecule, okay. Both can have the reaction happen, okay. So you only want one functional group has reaction, another has no reaction happen, okay. So you can do some reactions, okay, block one of the functional group you don't have reaction happen, okay. So and then you can do the reactions, okay, have the reaction happen, okay. So for example here, okay. So for both the benzene and those the amine can react with the kind of the ES kind of reagent, okay. And then we try to kind of block this the amine group, okay. So we react with kind of the acetyl chloride, okay. So that's pretty much similar like showed here, okay. Okay. And then convert the amine group into kind of amide, okay. So amide kind of the amine is much weaker nucleophile and also pretty much no basicities, okay, because the lone pair electrons can be shaped to kind of the oxygens, okay. So this kind of much milder kind of reagent, okay. And then no problem, you can go ahead do kind of the any kind of ES reactions, okay. Right, and then in the end case, so one important property for protecting group case. So after reaction, you can cleave off kind of the protecting group case. So protecting group in this case kind of we call the acetyl group case. And for this amine protect kind of the acetyl amine amide case, so we can use kind of the KOH potassium hydroxide case, and then cleave off give you back kind of H2 case. So overall, pretty much the So you have amine, okay, and then you protect with kind of the acyl chloride, okay. So normally most the common kind of the is the acetyl chloride, okay. All right. Okay, and then for you can go ahead do the ES reaction, doesn't matter what you want, okay. So profile, okay. Because this is still kind of also pair directors, okay, but the little bit bulky, okay. So we put the electron file onto its para positions, okay. Right. Okay, so once the reaction is done, okay, so you just apply something of your base, okay. Potassium hydroxide, okay, and then you cleave off the whole group here, okay. So that's what we call kind of protecting group, okay. And then give you back kind of amine, okay. and at the same time kind of you put the electron group on it, the electrophile on it. Okay. So that's the strategy kind of the protein group. Okay. So next chapter we'll learn more protein group. Okay. Right, and then second kind of protein group we already learned kind of in the previous class. Okay, so it's kind of sulfonase. Okay, sulfonase kind of can be used to kind of block kind of pair positions. Okay, and then you can do kind of also substitution. Okay, so remember kind of for the auto pair directors. Okay, can go either auto position or kind of the pair positions. Okay, so but if you only want kind of the starting group goes kind of auto positions. Okay, so you can do the sulfonation first. Okay, sulfonation okay block kind of the pair positions. Okay, and so then you do kind of ES reaction for this example. Okay, so not only kind of block one pair position, also block one auto positions. Okay, and then you do kind of bromination. Okay, and then put bromine on. Okay, and then under the aqueous kind of the high temperature the sulfuric acid. Okay, so you can cleave off kind of the sulfonate group. Okay, and that's the make sure kind of bromine only on kind of auto position to kind of OH group. Okay, so that's the pretty useful. We call kind of the residual control kind of protecting group. Okay, and then here's kind of one example. Okay, so use the both kind of the strategy. Okay, both kind of protecting group. Okay. So for example, okay, so we try to synthesis design kind of the converted the aniline okay, into kind of the also kind of nitro aniline okay, so put a nitro group on kind of also position of this aniline okay. So problem okay, so first kind of the amine group kind of the if we directly do it okay, so the sulfonate nitrogen reactions case, so we also sulfuric acid case, so we will kind of the deactive kind of amine group by proteination. Okay, activation reaction will happen first. Okay, and then second kind of this one only want to kind of put on the auto positions. Okay, don't want to put the pair positions. Okay, so that's hard. Okay, so third kind of over nitration case, so that's sometimes kind of if you have a strong activity group. Okay, like amine group. Okay, so sometimes cannot control to put only one nitro group on. Okay. So that's we can kind of protect kind of the amine group. Okay, also try to block kind of the pair positions. Okay, so use both strategy, both protecting group. Okay, so we do kind of protect kind of amine group first. Okay, because that still keep kind of it's the auto pair directors. Okay, so protect kind of amine okay with the acetyl kind of chloride. Okay, and then you use kind of the sulfuric acid. Okay, so control the amount. Okay, only block kind of pair position, only block pair positions. Okay, so now you have kind of deactivating group K and also the moderate kind of activating group K. So then you do nitration reactions. Okay, can control only add one nitro group bond. Okay, also because this the amide compound kind of amide group is kind of the strong activating group. Okay, so that's determine kind of the nitro groups still go kind of is the auto positions. Okay. Right, after reaction, okay, you can do deprotection, okay. So first use the dilute sulfuric acid, okay. So aqueous sulfuric acid, okay, cleave off kind of sulfonate group, okay, and then followed by kind of the OH group, okay, potassium hydroxide, cleave off kind of the protein on nitro, okay, amine, okay, and give you back kind of final product, okay. So that's actually kind of pretty nice kind of reaction route, okay. So all right. So later, okay, so we'll do a little bit of practice, okay, probably tomorrow, okay, so synthesis design questions, okay, so you'll need keep in mind these two synthesis strategy, okay. All right. Okay, so now we move to the second actually kind of another type of reactions, okay, for the benzene, okay, so aromatic compound, okay. So previously we learned all called kind of EAS reaction, okay, electrophilic aromatic substitution reactions, okay. Here we'll learn three kind of nucleophilic aromatic substitution reactions. Okay. So for the previous, okay, so we have kind of attacking species kind of electron file, okay, pulling electrons, okay. But for these three reactions, okay, so a nucleophile will be kind of attacking species, okay, nucleophile, okay, so will be attacking species, okay. All right, so the first one is kind of diazonium reactions, okay. also kind of called diazoxime kind of intermediate, okay. All right. So for this reaction, you have to use the aniline as starting material. You cannot use the other kind of aromatic compound, okay. So that's here the NH2K. Okay, so this one called kind of aniline K, only aniline K. So that's no different from kind of other the ES reaction. Other ES reaction, you can use any aromatic compound. Okay. So for diazoxime reaction, only this starting material. Okay. So for this reaction, okay, so actually two steps. Okay. The first step, okay, so we convert NH2 kind of to diazoxime ion. Okay. So that's pretty good link group. Okay. So we use kind of the sodium nitrite. Okay. So the sodium nitrite. Okay. And then under acid conditions. Okay. So that can convert it to kind of the diazoxime, okay. Yeah. So this is the ion, okay. So for diazoxime, okay, so we have pretty good link group, okay. That's already showed here, okay. So that's here the first step, okay. Once first step is done, okay, and then nucleophile come in, okay. Yeah. So this nucleophile kind of just attack this carbon and then kick off the diazoxime, okay, ion, okay. So diazoxime leave as kind of the nitrogen gas, okay, and nucleophile replace kind of the original kind of NH2, okay. Yeah, so that's the whole reaction process, okay. So two-step reaction, okay. So first convert kind of diazoxime, okay, and then second convert kind of nucleophile, okay. And then for this reaction, okay, so really depends what kind of the nucleophile, okay, we can convert to kind of all kinds of the substitute kind of bending, okay. And for this reaction, reaction mechanism are not required, okay, but you do need to remember kind of the intermediate and also final product, okay. Okay, so here maybe put you guys on another paper, okay. So for this reaction, okay, so the first step always same, okay. First step always same, okay. The most important kind of the second step, okay. So continue draw the first step, okay. So keep in mind, okay, so NO2, okay, so not nitrate, okay, so the nitrite, okay, nitrite, okay. You generate kind of the diazoxime, okay, so intermediate, okay. And then from here, okay, so really depends what's the nucleophile, okay. So if it's kind of you use the copper's kind of chloride, okay. So keep in mind kind of CuCl, okay, so no Cl2, okay, so this kind of copper 1, okay. You generate kind of the chloro bending, okay. And the similar situation, okay, so if you use kind of the copper's kind of bromide, okay, and then you generate kind of the bromo, the bending, okay. All right, and then let's see. Okay, so but if you want to get kind of iodide, okay, so you cannot use the copper's kind of salt, okay. Instead, we use the potassium iodide, okay. So that can give you kind of the iodo kind of the bromine, okay. And then falling kind of if you want to get kind of the fluorobending, okay. So you use this guy called kind of the tetrafluoro borate, okay. Okay. BF4 minus, okay, BF4 minus, okay. So this one can convert kind of the diazoxime I into kind of fluoro, okay. So BF4, okay. So remember called tetrafluoroborate, that's right, okay. Okay, and continue, okay. So if you use kind of aqueous acid conditions, okay. So acid with kind of aqueous, okay. So sometimes here you also need heat for this reaction. You can convert the OH group, okay. Okay, so generate kind of phenol, okay. So OH, okay. And then yeah, continue. Okay. So if we use kind of copper kind of the cyanide, okay. So CuCN, okay. So you can put a nitro group, okay, onto bending, okay. CN, okay. And then in the end, okay, so yeah, if you want to kind of just give you back kind of just pure bending, okay, so yeah, totally replace kind of amine or kind of diazonium kind of ion with kind of hydrogen, okay, so yeah, you can use these two conditions, okay. Almost kind of fit, okay. Either you can use sodium boron hydride, okay. Okay. Oh yeah, you can use this H3PO2. Okay, so this one we call kind of the hypophosphorus acid. Okay, hypophosphorus acid. Okay, so yeah, that's just kind of totally give you back kind of bending. Okay, yeah. All right. So that's the lot of reactions. Okay, so yeah, actually for the most valuable one. Okay, so I will see last kind of this 4K. Yeah. So yeah, aldo, fluoro, and also OH, and also nitrile group. Okay. So because these 4 compounds, you cannot prepare it through kind of EAS reaction. Okay. So yeah. And then for this one, last valuable, okay, because they're just kind of they put it back kind of hydrogen onto bending, okay, so didn't do any substitution, okay. These 2, okay, chloro and bromo, okay, you can use kind of the EAS reaction to prepare it, okay. So yeah, last year the something keep in mind, okay. Yeah, so there are another 2 kind of nucleophilic aromatic substitution reactions, okay. So yeah, we will study them kind of in the class on Friday, okay. All right, so any questions? Right. So if you have any questions, can you type in chat window? Okay. Anything about your lab or kind of the lecture or kind of your quiz, whatever. Okay. Stop the recorded video.